And now we have Moshe from RSIP, who's going to talk deeper about the best practices, how deep learning is helping out with pathology. So let's give him a round of applause.
Okay. Hi, everybody. My name is Moshe. Few words about my company. So RSIP Vision is basically an R&D house for computer vision and AI algorithms. We've been around for quite a large number of years. We're pretty modality agnostic and task agnostic. Many custom solutions for medical devices as well as for digital pathology and other type of AI and image analysis challenges. So today I'm going to talk specifically about our approach and the best practices that we have found to be useful for us and for our partners in digital pathology, specifically through an example of a multiplex challenge. So this is the general workflow. You have some data set. Big data set. Usually, you need to prepare it. Curate it throughout the bad examples, etc. You have initial training, and then you have some iterative retraining. As Hakima mentioned before, you're always in contact with some domain expert to get feedback on the results, reiterate both on your algorithms and your annotation, and get the result and do some validation. I'm going to talk specifically about a multiplex image analysis task. The reason I'm choosing it is because there are a few different tasks that need to be integrated in this kind of pipeline. So it's sort of an interesting way of seeing the different tools that we're using and how we're applying them. So in digital pathology, from the point of view, or from my point of view, as a computer vision guy, basically we're always looking for some cells and some regions of the image. We're looking to count them. We're looking to classify them into different types based on various channels of the image. So there's always an initial step of nuclei detection and segmentation. That's always going to be a critical step. So if your nuclei detection is not accurate enough, if you're merging too many nuclei, if you're not counting the correct ones, then it's going to throw the whole result off. There's also an initial step. The second bullet here is tumor segmentation. So you're usually looking for not only for local segmentation of the nuclei or of the cells, but you're also looking to segment specific regions of the image, usually looking for suspected cancerous regions. You're maybe segmenting other things besides nuclei, such as key markers. We get into that a bit later. And then you're doing, so after you've found these objects in the image, in this case it's cells, you're looking to classify these objects in some way. In this case, for multiplex image analysis, it's called cellular colocalization. So we're looking at the response on different fluorescent channels and using that to classify the cells. But again, we want to do it in a more holistic manner. We want to do it the way pathologists do it, not only to have all kinds of predetermined thresholds on the responses in different channels, but rather build a more general purpose, more scalable system that can tackle more difficult tasks. And then afterwards, you want to configure this to merge all the different results into a single cohesive output to be able to use, tabulate the results and use them for research and so forth. Okay, so we'll start with, maybe this should have been at the end, but we'll start with an overview of sort of how the pipeline works, how the solution works. So the input is a raw multiplex image. Sort of traditionally in this area, people do quite a bit of pre-processing of these images, to correct for crosstalk and to separate the channels better. We've actually found that usually it's better not to do an awful lot of that, but it probably depends on the conditions on which the images were taken, the variety of sources, etc. Then the first stage, we have nuclei detection, finding where the nuclei are before actually segmenting them and measuring them. In parallel, we do tumor segmentation. That's the second on the left for the tumor region. So that's segmentation, but it's at a very different length scale. You have key marker segmentation, looking for cytoplasm that's responding to various on various channels. After we have the initial detection steps, we do nuclei segmentation. We want to separate each nucleus from its neighbors, and this is a critical step in order to get your counts right and get your classifications right. And you have cell classification and combining all these outputs into a result, both in terms of presentation of the results so that they can be easily viewed, and also to do statistics. Okay, so as I said before, nuclei detection is a critical step in getting an accurate analysis of these images. Of course, there are many tools around that have been around for many years using various classical image processing methods. Some of these tools are very well entrenched in the market, and then you need to tweak many parameters, many thresholds. People are used to having this kind of control over their system. Some people might prefer to use this kind of system. I'm going to talk a bit about our approach. So this is a very challenging task. There's variations in shape, in size, in intensity. Sometimes a nucleus, the nuclei in a given image can have multiple scales of intensities. You want to pick up on all of them without hand tweaking it too much. They're merging and overlapping nuclei. It's hard to find all of them, and you always have the problem of what we say in Hebrew, we call it a short blanket. So if you're trying to do this with a classical rule-based system, the blanket is not going to cover all of the cases, no matter how hard you try. You try to make it more adaptive, you're going to miss some obvious cases. You try to make it more generalized, and you're going to miss some of the ones that you want to detect. So these are just some visual examples of the challenges. So sizes and shapes can vary very much. There are hollow nuclei, there are filled nuclei. These appear very different from each other. Those are the blue ones. You've got variations in intensity. So yeah, the lights are on, so maybe it's hard to see a lot of them. But suffice it to say that some of the green ones here are much weaker than the others. And you have merging and overlapping nuclei. You can have clumps of cells, and you want to separate them properly. And this is not a straightforward task by any means. These are just the same examples. And this is the kind of result we're looking for. A trained expert, sometimes even just common sense, but sometimes it takes really a pathologist, can understand from these images where each nucleus is based on their experience. And based on the human eye, but this is not a simple task to code in, a classical algorithm. And deep learning, as we all know, has been seeing many successes here. So classical image processing, you're doing thresholds, you're putting all kinds of physics-based models on the image, and in deep learning, you have your annotated data, which of course is a challenge. How do you generate this annotated data quickly? And you're teaching a neural network to learn the features from the data itself. And there can be also hybrid methods and post-processing that can be applied to the data. There are ways to combine these two approaches. But basically, we've been seeing over the last few years, we've really become converts to deep learning, as is most of the field. So overview of our approach. So basically, if I can put sort of a sort of slogan on this approach, we say unit-like data requirements with mask RCNN-like performance. So the basic idea after these code words of neural network architectures is you want to detect all of these nuclei, all of these cells, and you want to segment them. You want to do it hopefully fast, though that might be less important in most situations, but you also want to do it with as small data requirements as possible. Many detection architectures tend to be more data hungry than segmentation architectures. And actually what we found to do best, and there are infinite ways of doing this, what we found to work best is actually to sort of treat all the stages of this problem as a segmentation problem. I think this was mentioned in one of the questions in the earlier lectures, asking, did you try segmentation? So basically you can think of cell detection as a segmentation problem. It's not really segmentation. You're not trying to get a binary mask. You're trying to detect the centers of the cell. And this can be formulated also as an image-to-image transformation problem. You have a heat map that you put on your annotated data for the cell centers, and you train a sort of segmentation network with appropriate cost functions, etc., to detect the cell centers. And then you have your instances, you have your patches or your region proposals. So here it's not another network, you just use a patch around the center that you have found after you detect the peaks. And then in each patch, you train a different network to do instance segmentation. So you're training a network on smaller patches to find one and only one cell that's going to be always centered around that patch. And then you can integrate all of these results together. So this is the way it works. You have an image, and again, we found we don't really need, or it's not really advisable to do all that much pre-processing in most cases. You need annotation of your cell centers. So you would think this could be a very time-consuming process. Obviously, you don't want to pay a pathologist to mark these cell centers with their mouse one by one. The way we operate it is to have an annotation team of sort of semi-experts and have them guided by a pathologist, but you don't want your annotation team to work so hard in clicking all these cell centers as well, which which is why usually the best way to do it is sort of a bootstrapping approach. So you have some rough algorithm. It could be a classical algorithm using thresholding that you play around with a little bit. It can be a standard, even an open source tool, or it can be a neural network that you've trained maybe on very little data at first. You have these results, and then your annotators need to obviously throw out the errors and mark the ones that are missed, or maybe even identify only challenging regions and annotate those by hand, and that can save a lot of time. And this is key in developing these solutions quickly and robustly. You need to choose the right way to select the loss function here and the spatial weighting. But the architecture is based on pretty well-known standard segmentation architectures. An aside here is that the original UNET paper was actually also focused on separating cells that are touching each other. They took a different approach, which we have tried many times, but we find that this approach that I'm describing here of separating detection from segmentation is actually, in most cases, more effective. At prediction time, and sorry, you probably can't see the peaks here at all, you need to do some peak detection. So from the first stage of your network, you're just getting, you're not getting a binary mask, you're getting a grayscale image that's responding to peaks. And there's a little bit of post-processing here involved in defining what the height of a peak is and what's too close, what's not too close, because in the end you want just one individual center out of each of these peaks. And then you have your regions, you have your individual cells. The cell is always going to be centered in the patch. You need to take a patch that's still going to show some context. So you see in this case, you see a few cells in the patch, but the next network you're training is going to be trained on segmenting the cell that's in the center of the patch. And this actually works very well. The network learns how to ignore the cells that are not centered on the patch to separate the central cell from its neighbors. And this is also going to drive the failure cases. So once you know that, then you see you can sort of look at the failure cases of your network for segmentation, and you can see maybe they're adjacent to another cell of some other type. This can guide your failure-driven development of the solution as well. The next stage is instant segmentation, which is again another segmentation architecture. You need to tweak it again, as Hakima described, the human in the loop in the annotation process and the domain knowledge process. There's still human in the loop at every stage of developing a neural network. Everybody is trying to run to these platforms where it's all automated and just give me your data, we'll feed it into the cloud, and out comes a neural network. In practice, images are very different from each other. Each challenge is, so even if you're using the same basic toolkit, there's still a lot of I wouldn't call it, well, there's manual work in annotation as well, which you try to minimize, but there's also a lot of sort of accumulated human experience that needs to be put in to iterating on these solutions and getting a good result. These are some results of nuclei segmentation. Actually, these are results of the numbers up here for detection. So how do you measure detection? You don't want to just count the cells and then compare that to a ground truth count. You need to measure if you have found the cells in the location where you are looking for them. So you want to get to a number that's precision and recall in the end. How many cells have I correctly detected? How many cells have I missed? The way to do this, so there's a parameter here. You need to define some tolerance. You're not going to detect each and every cell at the same central pixel as the ground truth cell, but you can define some reasonable tolerance. You can measure afterwards how well your results have obeyed this tolerance, and then you count how many cells of the ground truth have I detected, say, to within 1 or 2 or 3 pixels, how many cells that the network has detected are being missed, and then you get your precision and recall numbers. In this case, we're quite happy with the results. We're getting 91% recall, which is better than all the baseline classical tools and industry standard tools that we've compared to, and a precision of 97%, which means if we detected a cell at a certain location, it's almost definitely there. We almost never detect false positive cells. Actually, along the way, when you're iterating this and various, you're doing a training set and a validation set and doing another version of the algorithm, you tend to find lots of errors in the ground truth annotation when you start to look at the network errors. So some of the errors you're going to find when you're developing the solution are really going to be errors of the neural network, and you need to think, try to get some insight on this. Sometimes you can, and sometimes you can't. Sometimes you say, yeah, I just want more data. Sometimes you have specific failure cases. There are always going to be failure modes in the reverse where you find errors in your annotation due to, thanks to your neural network. This is an example of nuclei segmentation. So just focusing on one of these clumps of cells, we can see it separates it very nicely. This is comparison to a classical tool. I think the name of it is a little bit later in the presentation. So first of all, our count is closer to the ground truth, but also the classical tool is not segmenting the cells properly. So many of the cells here are not separated from each other the way they should be based on the image itself. So there are detection metrics, and there also should be segmentation metrics. You need to have some test set of the segmentation and to measure how well your cell masks are actually overlapping with the individual cell masks in the ground truth. This is just another comparison. So the tool on the left, I think it's called Inform, not positive. So the counts, our count is more accurate, but also the tool on the left is just not segmenting, not separating this clump of cells correctly. You can see in the center panel, this is quite a challenging clump of cells. It takes some domain knowledge, some experience with these images to actually understand where each nucleus is. But if you look closely, you can see that the purple result on the right is actually the way that these nuclei should be separated from each other, and classical watershed type methods are just going to fail. These are more comparisons, basically the same idea. So again, a rule-based system is not going to get the overlap and the touching cells right. It's going to be very difficult to define the correct thresholds, and by feeding data into deep learning, this is really the way to go. This is another comparison. Okay. I'll go on to the next test. This is tumor region of interest segmentation. So now we're looking for regions of the image which are suspected tumor regions or some other region of interest. So it's a very different task in the sense that you're not looking for individual blobs in an image. So I'm saying from a computer vision guy's perspective, you're looking for, you sort of need to zoom out, to squint, and to look at the areas, but you still want it to be accurate. You still want to get holes in this region correctly. So here, again, the architecture itself is actually pretty similar. It's also a segmentation task. You're just training it on a different type of ground truth. What's interesting here is how to get the data annotated and how much data you need annotated. Because if you don't have enough slides, then the network's not going to learn. It still takes a lot of annotation. And again, here, classical algorithms are actually your friend because you can sort of hand tweak locally the classical algorithms to get a decent result. You can correct that. You don't even have to be too sort of obsessive about correcting it perfectly in all areas, because what we find is that after you take this even noisy data, training data, and feed it into a neural network, the network's going to generalize better than the noisy training data. So you do need to, you can't just feed it in as is. You do need to correct it, but less than we found that we need to correct it less than we were expecting, and these networks are learning to generalize over the noise. Key marker segmentation. So in this specific case, you can't only look for nuclei. There's another dye called the CD68 that's dyeing the cytoplasm of a certain type of cells, and some of the cells, their nuclei are not presenting at all in the nuclei stain. So this is a different neural network, and these results need to be merged and combined for cell detection. Similar methodologies. And then we get to cell classification. So, or what's called in the field, in this profession, colocalization. So this is a multiplex image, which means we have multiple dyes that are fluorescing in different wavelengths. These are captured. It comes to us, to our algorithm, as an image with multiple channels. The colorful image is just a way of displaying it. Typically, the way these cells are classified, so you have a pathologist who knows what they're looking at. They know what they're looking for. They can explain it. They can train an annotation team to reasonably annotate this. In the past, the way this was done was by sort of turning these intuitions of the domain knowledge expert into a set of rules. So you have a threshold in one channel, maybe an intensity, maybe a percentage, maybe in both. What happens is some combination of both. You combine these channels and use it to classify these cells. If it's an easy case like that, then maybe a classical algorithm will work. Maybe you want to do better than that. You want to annotate it. It'll be easy to train your annotation team. In more subtle cases, they can still be annotated by a human, but rule-based systems are not going to work. And then maybe you'll need an expert to do more of the annotation themselves, of clicking on each cell and selecting the proper cell type. Maybe you'll need more extensive training your annotation team. Maybe you'll have more errors. You'll need to invest more human results. So always the R&D effort for this type of solution is going to be a combination of the domain knowledge, of manpower that's semi-specialized, like people who have some motivation, some background in biology, but not necessarily pathologists themselves that are doing most of the legwork for the annotation, and you have an expert supervising it. And, of course, of the R&D team who's tweaking the neural networks, retraining, and especially doing failure analysis. In the end, the architecture of the network is a classification network, so you have various layers of convolutions. You introduce nonlinearity in the middle, the usual tricks of the trade for regularization, for data augmentation, etc. Actually, the data augmentation becomes very important in the failure analysis part of the R&D. So once you see where your network is failing, it's very important actually to understand these cases. It's not just a black box, because once you understand these cases, in your next training session, you can show the network more examples of the difficult cases. You can try to artificially create more examples of the things that the network is having trouble with. So you really need sort of to do this in a deliberate manner. You can't just throw more and more data at the problem. You need to understand what the failures are, and to sort of grow your network's knowledge by training it on the proper selection of examples. This is an example of classification results. So in this case, we had 3 cell types and other 4 cell types. So other, it can contain a whole grab bag of different cell types. This is before the finer grain classification of this data set. And again, this is it wasn't all that big data set, but many cells. So there, I think about 40 slides. Each slide contained many images. So hundreds of thousands of cells in this data set. You don't need to annotate nearly that much to get a good result, and you can test it on all the others that you haven't annotated yourself. You can pull up test sets to your heart's desire to verify and re-verify this algorithm. And the accuracy is 94 to 98%, depending on the cell type, including other, which is in many cases challenging in general in AI and also in digital pathology. Sometimes if you have your other class, then you're going to need to start breaking it down. Somebody here before mentioned multitask learning. So in many cases, it's not enough to have 4 classes. You have to force the network to learn more about what distinguishes subclasses of other from whatever classes it is that you're trying to attack under the task. Yeah, how much time do I have? I've got about, I got five more minutes or so. Yeah, okay. So, I hope this gave a good taste of how we approach solving these problems. Probably many people here also live this field day in and day out. Just a few more examples, sort of related examples of how AI can be used in digital pathology. And again, we're not using this only for digital pathology. We're doing 3D segmentation. We're doing tasks that are not segmentation tasks. We're not shoehorning everything into segmentation. Obviously, this is a very powerful tool, but just some more examples from digital pathology. So this is a different cell classification task using different marker layers. Again, different dyes, but it's the same kind of idea and the same kind of challenges of detecting the cells and overcoming these holes and these sort of difficult to separate examples. This is, again, classification, different cell types. Actually, I'll show this one at the end. Yeah, it's here. Okay, so in this, this is a completely different data set, completely different modality. It's not multiplex, etc. We've got 2 stains, but basically what distinguishes these 2 cell types is degranulated versus non-degranulated. So the cancerous cells, their cytoplasm becomes degranulated. And this is, so you could, in the past, one could have tried to define filters to pick this up by hand, like say, okay, this is going to respond to these higher frequencies in this way, or try to handcraft an algorithm, it would be very difficult to get a robust result. And the neural network obviously is learning hundreds or thousands of filters, and it's learning it from massive amounts of data. And this task has become a tractable task, which it really wasn't in the past. This is a different example of dot counting and of overlapping cells. So you can teach the segmentation network and add some post-processing to figure out where the cells overlap. So in the lower right and the upper right, you can see that the borders of the cells do not have to be mutually exclusive. And this is a natural way to use this tool. This is a different example. I think this is mouse, I'm not sure, of segmentation tumor region of interest. So it's mostly just the accumulation of the responses to these nuclei. And this is trained versus pathologist ground truth annotations. Okay, conclusion. So I guess you got the message. The role of AI is to bring image analysis applications. We know all this. The solution development time is really much faster. It's much more efficient. It's more accurate, and it's able to tackle more complex and challenging tasks that really weren't possible in the past. Which is, I guess, why we're all here. So thank you very much.
Questions?
Hi.
Thank you for your talk.
Sure.
I had a question. So you were measuring accuracy based on the counts of the cells.
Detection, yeah.
Why do you need to segment them? What is that used for? The actual segmentation rather than just detecting the centers and counting them that way?
Mm-hmm. So sometimes it's helpful to do joint classification and segmentation. You actually want to train the same network to do segmentation of the cells and to do classification. In other cases, you're right, and it's enough to do classification based on a patch. But in some cases, what you find is effective is either to do joint training or to force your classification network to only look at, something that's close enough to the nucleus that you have found. Yeah. So it depends.
Hi, thank you. So the neural networks that you use, do you build them from scratch, or do you pick something off the shelf and just tune the hyperparameters to this particular problem?
Yeah, so it's not off the shelf, but we don't build them from scratch either, which means there's plenty of literature. The architectures that we used are based on well-known architectures, but it's not an off-the-shelf platform like Google AI or whatever. I mean, we work with Keras and TensorFlow. We don't write the layers ourselves because there's no need, but there's lots of sort of nuances and details that go into the network architecture and the type of ways you try to overcome overfitting and issues such as that. And more than that, even many nuances that go into the training process of the network. What type of examples to show it, how to do the augmentation, etc. So we don't think it's good enough to use an off-the-shelf platform. But the technology itself and the libraries itself that are used for it are, very accessible.
Mic's off, but if you just want to go loud for that.
Okay.
Sure.
For the multitask learning, you have different type of cells, and sometimes, I think in many cases, there's a type of cells that are very abundant, but others are very rare.
Yeah.
In that case, deep learning really low efficient. Why not combine this different cell classification?
Yeah, so the type of solution I described now, which is the go-to for tasks. So if the cells are too rare, if you really have very little positive examples of the type that you're trying to pick up, then you're in trouble. You need to figure out something else. You need to do anomaly detection. It becomes a more challenging task technologically. There are ways to go around it with different classes of solutions that I've not described here. You can train a network to detect anomalies to only on one class of examples, and you try to pick up things that are different from that. That might be helpful. If the data set is too small, then yeah, you're stuck. If the data set is big enough, and big enough does not have to be all that big for this kind of classification task, maybe it's not measured in the tens or hundreds of thousands, it's probably measured in the thousands to get a good result. Could be less, then then you need to balance the training data appropriately. You don't want to train your network on a completely unbalanced data set, so you can throw only some of the negative examples at it. If you have a decent amount of examples of the cells you're trying to classify, then the imbalance in the data set can be overcome, and the wealth of negative examples can be an advantage. It doesn't have to hurt. If there's too few, then yeah, you might want to go for something else, or to maybe you want to keep your human in the loop. If there's so few of them, that's difficult. You'd probably go for anomaly detection. You'd probably do anomaly detection and then have a human classify the few anomalies you'd pick up.
All right, let's give a round of applause for Moshe. Thanks so much for your presentation.